in this video short, I'm going to be talking about buffers, and there is so much information. I could talk about buffers probably for 2 hours and work problem after problem, so I'm going to do my best to streamline that information to something that you can relate to and use to help you solve some of the homework problems. So buffers are compounds that are resistant to changes in pH. Our bodies have two main buffering systems. Our blood has its own buffer system, which is carbonic acid, and our tissues have a separate buffer system, which is the phosphate buffer system. So just two different compounds that buffer and help stabilize the pH of our bodies. When I say the word pH equals the negative log of the concentration of H+ ions. Okay? Small p is just the negative log. So whenever you see a small p or a lowercase p, that just means negative log, and the H stands for the H+ concentration. Okay? So if we think about the pH scale, actually I'm just going to leave that there. pH scale runs from 0 to 14, and right in the center is 7, which is considered neutral. So water, purified water, should be pH 7. Now, as you decrease the pH, you are becoming more acidic. Okay? And if you were to increase the pH of any solution, you would say that's more basic. Okay? Our stomachs, just for fun, have a pH of about 2, so that really low pH helps denature the food that you've just eaten. It essentially turns the protein molecules into long, thin strips of spaghetti so that your body can start cutting that strip down into the individual amino acids, so you could absorb those amino acid building blocks and build your own proteins out of them. Basic compounds tend to be more like ammonia, which could be found in Windex. I mean, it has that horrendous smell, ammonia. And soaps. Soaps are also very basic compounds that we use to wash our hands with all the time. So a pH of 7, right? So if I were to come over here and plug this into my equation, I would say 7 equals negative log of H+. And maybe you're wondering, what is the pH of 7? What is the concentration of H+ ions if the solution has a pH of 7? So in order to mathematically do that, I would divide, well, to get rid of a log, you have to do 10 to the, so 10 to the, and there's that negative sign, so I need to remove that negative sign. So if I divide by -1, right, and I divide that by -1, I get a -7 there. So 10 to the -7 is equal to 1e -7. So 1e -7 molar, remember concentration has units of molar, which is capital M, which is just moles over liters. Okay. So 1e -7 molar is the concentration of H+ ions in water. If I have a pH of 2, the concentration of H+ ions is 1e -2 molar. Don't believe me? Take the negative log of 1e -2 and see what you get. You'll get the number 2. Okay, so that's kind of just working basic solving for pH and identifying what's the concentration of H+ ions. But how does that help us relate things to what buffers are? So again, buffers are compounds that are resistant to changes in pH. So in order to do that, they tend to absorb or consume H+ ions. Because remember, the amount of H+ ions in solution tend to tell you how acidic or basic that solution is. All right, so if I have an acid, let's take acetic acid for example. So this is the 5% acetic acid solution dissolved in water is vinegar. If I have an acid, and so my acid here, look at this functional group, we should know, that's a carboxylic acid functional group. I react that with water. What I'm going to get is I'm going to get an acetate ion and an H3O+. So a water molecule picks up an extra proton and I get a hydronium ion, H3O+, which is just usually simplified into H+. Okay, so these two are interchangeable. For simplicity's sake, I'm just going to stick with H+. Okay. All right. So acids, so remember this was acetic acid. Acids are proton donors. They donate protons to solutions, to the solution. All right. So that proton specifically is this hydrogen right here that's bound to that oxygen. Right? There's that hydrogen. And then that oxygen then takes on a negative charge because of the valence number of electrons is 1 over what it should be. So when you are naming these compounds, though, and you see this again and again and again, is that the acid usually has the ending ic acid, all right? And then it turns into the conjugate base, which you drop the ic acid and you add ate as the ending. So acetic acid turns into acetate. If you use formic acid, it would turn into formate. If you use nitric acid, you would have the conjugate base being nitrate. Okay? So that's just a little bit about the common naming that you see from when you're looking at these reactions of acids being dissolved in water. Okay? The other thing to mention is that these, you can write a KEQ for these reactions, but typically at equilibrium, it's just a different nomenclature name where it's just Ka, A for acid. So it's the exact same thing. The KEQ is equal to the Ka, but we just use A for acid. And if it was a base, we would be using B for base. But again, it's the concentration of products over reactants, which in this case would be the concentration of acetate times the concentration of H+ over the concentration of acetic acid. Okay. That Ka has a value of, I believe it's 4.75. I'm pulling this from memory, E -5. That is the equilibrium constant Ka. So given that this Ka value is a value that's grossly under 1, the number 1, that means that this reaction favors the reactant side. So probably if I had to guess, I would say 99.8% of the acetic acid molecule is tied up in the carboxylic acid portion, and probably only 0.2 or 0.02% had been dissociated to the acetate. That's what this value is letting me know. Remember, if the KEQ is less than 1, that means that your reaction favors the reactant side. Okay. These numbers are hard to kind of visualize, though, so what we can do is we can talk about what's the pKa of this value. And remember, p just means take the negative log, right? Some lowercase p just means take the negative log of whatever. And so I'm going to take the negative log of the Ka, and that is it's not 4 point, it's 1.8. That's what it is. All right, sorry, my memory is coming back. It's 1.8 E -5. So if I take the negative log of 1.8 E -5, I should get a value that's 4.75. That's where that 4 was coming from. That's the pKa of acetic acid. Sorry, again, I'm pulling this from memory. All right, so the pKa is 4.75. And this number, it's a very interesting number. As far as the pH scale goes, so remember my pH scale from 0 to 14 with 7 being neutral, I could plop this number on my pH scale at 4.75, and that just lets me know that acetic acid, it's an acid, and if I had equal amounts of that the acid and conjugate base, my pH would be 4.75. Okay, so one thing about buffers, acetic acid is a buffer. It buffers really well, which is we call this the buffer range. It buffers really well, plus or minus 1 pH unit from the pKa. So if I wanted to buffer for acetic acid, acetic acid makes a really good buffer for things that go up to 5.75 pH units and down to 3.75 pH units. Okay. So it's really good at resisting changes in pH if you want your pH to fall within this region, this zone. And in your textbooks, there's a chart of common acids that have the pKa values. And so if you were asked to choose an acid to buffer a solution at a certain pH, you just want to look at the pKa values of those acids and make sure you're within the plus or minus 1 pH unit from that pKa value. So talking about all this reminds me of the very last thing I wanted to mention, which is the Henderson-Hasselbach equation. This is an amazing and incredibly useful equation that is pH equals pKa plus log A minus over HA. So, and this would be concentrations here. So, what is HA and A minus? Haven't really told you what that is yet. So, HA, if this goes with the idea of general nomenclature for things. So, if HA is the protonated acid form, so that's the acid, and A minus is the conjugate base. Remember, when I had acetic acid and it broke down into acetate and an H plus, there's my A minus, right? It has the negative charge. And this compound, my acetic acid, is my HA. H is just the proton. It's the protonated form that's ready to be donated. So you can use this equation to help solve for the pH of a solution, because you know what the pKa is. That's a given. That'll be given to you, or it's in a chart. That's a known. And then you can determine what are the concentrations of A minus and HA in solution, plug it into this equation, and it'll tell you what's the pH of your solution. So remember the Henderson-Hasselbach equation, which is pH equals pick a log, aha! So pH equals pick a log, aha. So I'll have a few of those questions on your homework so you can practice using the Henderson-Hasselbach equation. You'll likely also have to calculate, let's zoom out here, what did we cover? Calculate maybe the concentrations of H plus or acetic acid using the Ka equation. And last but not least, likely I'll have you also practice calculating the pHs given an H plus concentration. So that summarizes acids or buffers and acid-base problems for Chapter 12.